Hi, this is Professor Cummings, and I want to make a continuation on our Strength of Materials series. This will also be added to the playlist as well as to the engineer's reference. And in this particular one, I want to go over a concept that I touched on in the last video on axial loading and displacement, and that is superposition. So before I get too far into the example, I want to make sure I define this word. So what is superposition? Now, superposition is a concept that exists in all sorts of technical and STEM-related disciplines, and it's I want to go through a few of the examples, and I want you to see what the commonality is between all the examples. So, in physics, whenever two or more waves, talking about waves, traveling through the same medium or at the same time, the waves pass through each other without being disturbed. The net displacement, of the medium at any point in space or time is simply the sum of the individual wave displacements. Alright, so in physics, when talking about waves, superposition says that the net displacement is the sum of the individual wave displacements. And you can see this, this is something I pulled up off of Google. You've got two sets of waves. You've got a set of waves that are pretty well in sync with each other, and when added together, their overall displacement is doubled. And you got two waves that are actually opposing one another, and they have a net displacement of 0. And on an oscilloscope, you can see that if you look at the blue wave and the green wave, that you can take that as a sum to get you what you see on the red wave. So that is superposition in physics. So this plus this is equal to this. Now, in electrical applications, in electrical engineering, for a linear system, the response, voltage or current, so we're talking about either voltage or current, in any branch of a bilateral linear circuit having more than one independent source equals the algebraic sum of the responses, voltage or current, caused by each independent source acting alone. So again, if you've got a circuit and you've got two independent sources, the overall current is going to be the sum caused by each one of those sources. So you could look at this particular set of circuits, and in this one you do have two power sources, and as they come across these two circuits, across this particular resistor, the current is actually the sum caused by these two sources. So again, you've got a linear system, you've got two independent sources, and you've got a common area that they come across, and the sum, or the net result, is the sum, the algebraic sum of the two different responses. So you can start seeing a pattern here. Now let's look at strength of materials. So something that you'll see as a mechanical engineer or a civil engineer. So strength of materials. How does that same concept apply to something like this? Now a little bit longer, but a little plainer language. A method used to solve complex problems with multiple loads, put that in red, multiple loads, and or reactions acting on a member. Superposition helps us solve these problems by breaking the member down in as many times as necessary for each force acting on it. Okay, it being the member, each force acting on it. All of the stresses and deflections for that point of interest are found. They can be added together to get a final answer. And the only thing, I got this definition off of a site online, and the only thing I would change is I would say displacement or linear displacement, but they all come back to the same thing, since that's what we're ultimately talking about in this particular video. Can all be together to get the final answer. So again, you've got another summing of things to get you your final answer of independent forces or independent loads. Now, in this particular example, they're showing, if you had a beam, a member, and it's got a distributed load and a concentrated load, the net result would be as if you had both of those loads on the same member. Now, another way of looking at this, since we were talking about axial loading, that was the last video I did was on axial loading, what you can take a slightly different twist on the definition. The resultant stress or displacement in the final answer at a point can be determined by algebraically summing the stress or displacement caused by each load, or each load component applied separately to the member. Now that is a little more in line with what we're talking about. Still follows the same principle, it's the same concept, but now it's just applied to axial loading, our definition of axial loading. So look at this little thing I pulled up, this little illustration. So we've got a member that is bolted to the wall, so it is actually fixed to the wall. You can see it here, fixed to the wall, and you have, a steel segment, an aluminum segment, and a bronze segment. They each have their own specific area, and they all have their own length. So 2.5 meters and 500 square millimeters for steel, 2 meters for aluminum, along with a 400 millimeter square area on that segment, and on the bronze is 200 millimeters square and 1.5 meters. Now, hopefully this starts looking a little familiar when you consider we're talking about displacement. We also have various loads. We've got a load of P on the aluminum segment. Going into tension, we've got 2P going on to the bronze, and we have 4P working on the steel. So we've got a load for each segment. We've got a length for each segment. We've got an area for each segment. And since we've got different types of material, we have a modulus of elasticity that has to be applied to each one of those segments. And then we can find the displacement. So if we want to know, just looking at superposition, what the displacement was at any point, say here, we would have to know the sum of the displacements of each one of these segments. And we can do that. We have enough information that we can find the displacement of each one of these segments and find out how much each one of those contribute to making this point move outward or possibly being compressed. We don't know. We don't know how, because we don't know right off the top of my head what the modulus of elasticity of each one of those or how they correspond to their relative lengths and their area. So until we work through the numbers, we don't know which direction this point's going to go, but we do know one thing about it is that it's going to be the sum of all three of those segments, those different load components. So again, this is the equation for displacement. And I'll say mechanical displacement from last time, and this is, that segment, that little illustration, and all we're doing is we're going to see these different components. If you want to know what is going on at this particular point, like I said before, at the end, it's going to be the steel, the displacement of the aluminum, the displacement of the bronze, and that gives you what you're going to do. So here is an example. So let's just go ahead and illustrate this, or use this example to help illustrate the point. Both of linear displacement, there's another example for that one, but more specifically, the whole concept of superposition, the principle of superposition. So let's see, let's go. We got a steel rod, A992 steel rod is subjected to loading shown. So we got this steel rod, it's broken up into different segments, a point D, a point C, a point B, and down at the end a point A. And the loading, it's got 10 kilonewtons on the very end at A. It's got 5 kilonewtons going off in two different directions, two separate on these two collars, 4, 5, 3 triangles. And at C, we've got another 6 kilonewtons going in 2 points at 45-degree angles with the horizon. And they're got a length of each one, 0.75 meters, 1.5 meters, and 1 meter. So you've got 3 different segments, 3 different load components, and we've got different types of loading, and we're going to have to know we're going to have to break this up into different components and find out what's going on here. So let's finish off what they're given. So an A992 steel rod is subjected to the loading shown if the cross-sectional area, so we've got a cross-sectional area, is 80 millimeters squared. Determine the displacement of B. So what's going on at B? The displacement of B and the displacement of A. Okay, so that's what we're looking at. So neglect the size of the coupling. So basically we're looking at the coupling as it's a long rod, not changing the area. Neglect the size of the couplings at B and C, and they gave us the modulus of elasticity of 200 gigapascals. Okay, so let's see, let's put together again just a good practice of solving a problem like this. Set up what you're given. We have the area, we have the modulus of elasticity, and we do have all the loadings that's captured in our diagram. And for the sake of this, I'm saying that I'm going to assume that going upward is positive. We're going to have to figure out how much force is going in the y direction. And the reason it's just the y direction as opposed to y and x is simply because it's axially loaded and it's only moving in the y direction. That's the only place we're going to get a displacement. So we're here to find the displacement of A and B. All right, so now it's written out nice and neat. And my coordinate system is showing that I'm going to say A is in the positive. So what's going on inside of the segment is in the positive. Now my logic to this problem, since I know what I'm looking for, I know I'm looking for the displacement. And I've been given a whole lot of information, maybe not everything spelled out totally nicely, but enough information to start going. I'm going to need a certain logic, a path to take in order to solve this. So the first thing I'm going to have to do, as I was showing before, I'm going to figure out what the y component of the force is. Again, these two are going off at angles, as well as all the forces are going off at angles except for what's going at A. It's totally in the y direction, and I'm going to need the y component of each one of these. So this one I'm going to need the sine of 45 degrees times 6 kilonewton, and here I'm going to have to take 4/5 to get the y component of the 5 kilonewtons, and then I'll have to double since I've got those forces in 2 directions. So I'm going to have a y component from this 6 kilonewtons and a y component of this 6 kilonewtons and a y component of this 5 kilonewtons happening at B and a y component of the other 5 kilonewton happening at B. So first thing I have to do is I'm going to have to make sure I understand that. I'm going to have to use the method of sections, because I'm going to have to figure out what the internal reaction or load going on in each one of these segments. That's going to help me know since I know what type of load is going to be reacting in each one of these segments, now I can start to figure out a little bit more about what the displacement's happening. And then from there, I will finally be able to find the displacement in each section of the rod. So that's my logic. Get the y components, and those are the forces. Use the method of sections in order to understand the internal reactions, and then finally get the displacement. So as you can see, I'm going to look for the internal loading of P. If each one, I've got the length, I've been given an area, and I've been given the modulus of elasticity. Area and modulus of elasticity is consistent throughout this rod. And for the displacement of B, I'm going to have to use superposition of the different segments that contribute. And for A, again, I'm going to use superposition for all the segments that contribute. So again, looking at the method of sections, I've got section AB covered here, segment contributing from up to BC here, internal. So again, working from the end backwards. So this is segment BC and an internal reaction here. So there's going to be an internal load of, what is that? That's AB, an internal load for BC. And this one is taking it all the way back to the last segment, which is going to be an internal load of CD. So this is what I'm going to have to find. So that's what my method of section is telling me. I'll handle each one of these separately, and this, once I use my sum of forces in the y direction, that'll help me understand what P is, the load is for each one of those segments. So looking at each one of those, again, keeping my coordinate system in mind, so I can take anything pulling down as negative and what's reacting back as positive. I look at the first segment, sum of forces is going to be 0. Sum of forces in the y is 0, assuming this thing is in equilibrium. And the load in AB, reaction in AB, is just going to be the difference between that and 10 kilonewtons, meaning it is just going to be 10 kilonewtons. So that is the first load. The second one is going to be the sum of the forces. This is going to be the sum of these three forces, the y component of those three forces. So I've got the reaction at BC minus twice the 5 kilonewtons and 4/5 triangle minus the 10 kilonewtons that has to be added in as well equals 0, and the reaction in segment BC is 18 kilonewtons. So we've got 2 down, 1 to go. And for this third one, again, the reaction in segment CD is going positive, and the segment at C, the load at C, is 2 times 6 kilonewtons and the sine of 45 minus twice 5 kilonewtons and 4/5 minus the original 10 kilonewtons down at A is going to equal to 0, and that just tells us that segment CD has an internal reaction of 26.485 kilonewtons. So I've got reaction loads now. So I've got reaction loads, I've got lengths, I've got modulus of elasticity, and I have area. So let's consolidate all that information. I've got all my internal loads, I've got the area, I've got the modulus of elasticity, and again, both of these are common for every segment. That's going to become important as to how we solve this problem. Both of those are common throughout the segment. This is basically a consistent pole, and we will be able to find our displacement now for each one of those segments using the principle of superposition. So we got the principle of superposition, and in order to know what is going on at A as well as what's going on at B, you're going to have to find the displacement at each one of these, segments, to find out how much these points are moving. So the displacement at B is going to equal to the displacement of segment CD plus the displacement at segment BC, CD, BC, and the displacement of A is going to have to equal to the sum of CD, BC, as well as AB, so all three of the segments. So if we just start with segment B first, we have, again, a load, a length, a modulus of elasticity, an area that's going to factor out, and then this quantity plus B, or the load at CB that we calculated, as well as the length of CB, which we were given. We put this together, plug in all of our numbers, and we can see from this loading, and it makes sense that it's going down. It's actually traveling down about almost 3 millimeters, 0.00293 meters, which is about 3 millimeters at segment B. So that's what segment B is doing. It's moving about 3 millimeters down. So it's stretching. It makes sense because these are all downward, biased downward load. Now, in order to find out what's going on at B, we need to find out what these two segments are doing plus what's going on at AB. So that's going to give us the displacement of A, what's going on there. So A is going to be the displacement of AB, load, length, area, modulus of elasticity, plus the displacement of B, which we already just calculated. And that comes out to, again, about 3.5 millimeters, or 0.00355 meters going downward. So again, this is Professor Cummings, And I would, plan on going into different types of now fixing or how those members are set up. So looking at between determinate and indeterminate members, and I'll give you a definition and I'll further work through some examples. Thanks for watching.